Hello, I am Dr. Rashid Ahmed from the Department of Physics of Kohat University of Science and Technology. In the subject of Mathematical Methods of Physics 2 with the course code PHY 222, we are at the lecture number 8 and the topic is Fourier Transforms. In my previous lectures, I have been developing the method of Fourier series by expanding the periodic and continuous functions into sines and cosines. This has applications, Fourier series has applications in many physical problems. For example, in light waves, where light is composed of different frequencies and wavelengths, and we can represent these wavelengths as terms of Fourier series, and then we can analyze them and can compute the more physically relevant wavelengths or more important wavelengths. The second example is of the sound waves, where the different harmonics involved in sound waves can be computed or can be represented as the terms of the Fourier series. And similarly, in electricity, Fourier series can represent the different voltages, AC voltages involved in some particular problem. So Fourier series is an important tool with the help of which, a mathematical tool with the help of which we can analyze different physical problems. But then question arises that can we extend or modify method of Fourier series to the case of non-periodic and continuous functions? And answer to this question is actually yes, and we can do this by the use of Fourier transforms. So by now you might have guessed that Fourier transforms are actually a method or extended method of Fourier series used for continuous and non-periodic functions. So in today's lecture, I will explain to you that how we can use Fourier transforms for continuous and non-periodic functions. So let's begin this by reviewing these two important questions which arise to us when we are doing the Fourier series. The first one is that can we represent a function which is not periodic by something analogous to Fourier series? And the answer to it is yes, and we can do this with the help of Fourier transforms or Fourier integrals. How we can do this? We will learn this into today's lecture. And the second question is, can we extend or modify Fourier series to cover the case of continuous functions? Again, the answer is yes, and both of these things, that is the non-periodic and continuous functions, can be dealt with the help of Fourier transforms. So what are then Fourier transforms and how they actually look like? Let me give you straight away the definition of these Fourier transforms. And as you might have guessed already, that these Fourier transforms would look like something integral, because we are talking about something continuous. So here you see two integrals, some convenient factor of 1 over 2 pi, which by the way could be splitted between these two functions, f of x and g of alpha. And then you see some coefficients here, these are functions as well, and some exponentials. One has the negative sign, and it is integrated over d alpha and it is integrated over dx. So probably you are comparing them now with the discrete Fourier series, where we had some coefficients, and this comparison is actually valid one, and in a moment I will show you that they are really comparable. And by this comparison is actually you will understand that how we can define Fourier transforms in this way. Okay, so let me first remind you the complex Fourier series formulas, and we are now talking about the period of 2L. Remember that initially in previous lectures I talked about the period of 2 pi, which were just a convenient choice, but now we are extended it to the more general case where the period is of 2L. And if you recall that the Fourier series expansion of any function was like this, going from minus infinity to plus infinity, Cn, and this was actually we are talking about the exponential case and not the sine and cosine case, and this exponential and also the period of 2L, not 2 pi. If you take the period of 2 pi, then this L will not be over here. And then these coefficients Cn were something like that. This was a general term formula, if you remember, we have derived for the coefficients of the Fourier series. So the whole thing was that we can expand a function into a Fourier series, and then we can compute the coefficients, and then we can analyze any physical problem with the help of these the relative importance of these coefficients. So as I told you that we are now comparing the periodic case with the non-periodic case, and this is valid comparison because it will give a sense of these continuous case that these integrals are correct. So let us do it this comparison. So first of all, let me write to you this continuous case and then the discrete case, and now you can see that this G alpha is actually something comparable to these coefficients Cn. So G alphas are playing the role of these Fourier coefficients over here, and this alpha is actually the continuous analog of this integral valued number or function n. So we are replacing now n with alpha, something alpha is continuous, and the Cn's Fourier coefficients with these G alpha, which are the functions. And you see another obvious thing, which is the integral. Whenever you are talking about something continuous and you are adding it, then you remember that this summation sign is replaced, the sum is replaced with the integral. So from this comparison, now you might be able to see that how this continuous thing for non-periodic functions is just an extension or modification of this discrete and periodic thing. So if now we can apply the methods we have developed for the discrete and non-periodic case to the continuous and non-periodic case, then it means that we have extended the methods of Fourier series to the continuous and non-periodic case. So these two things over here is called are called Fourier transforms, Fourier transforms of each other, and we will be talking more about them now. And okay, after developing this comparison, first thing is that f of x and g of alpha are now called pair of Fourier transforms, as you have already seen, and f of x is actually a Fourier transform of g of alpha, and g of alpha is the inverse Fourier transform of f of x. Well, as a matter of fact, these definitions are not that strict. You can say that g of alpha is a Fourier transform of f of alpha and f of x, and f of x is its inverse. So it's just the matter of choice, as you might have seen also in the formulas where they are totally symmetric. So one can call f as a Fourier transform and g as an inverse of it, or g as a Fourier transform and f of inverse of it. Only if you seen this into the formula, that the factor of 1 over 2 pi, but this is also not 1 over 2 pi factor was present in the g alpha definition, but since it's just a matter of definition, you can split it and can write 1 over 2 pi under root with both of them, and then it will make it completely symmetric, and then it's just a matter of choice which one is a Fourier transform and which one is inverse of it. Okay, so after completing this definition of Fourier transforms, it's now important to see that the whole procedure of the Fourier series can be brought in over here to the Fourier transforms. By this I mean that if you remember in the Fourier series, if I go back, in Fourier series what we were doing actually is expanding a function f in terms of this series and then computing Cn and putting back these Cn over here and explicitly knowing the function and its different terms. Similarly, can we do this that if we compute, for example, for the Fourier series, for the Fourier transforms, the g alphas and put back them into the f of x, for example, over here, that we compute the g alphas from this formula and put it back into here and know the complete and explicit form of f of x. So this is what I want to show you now, that it is really true. And let me do this. So first of all, I will make a change of variable in f of x, and will also let the period to increase from minus L to plus L. So I will change this period from minus L to plus L to infinity, so that to make it look like continuous, and also make a one change of variable over here to make it look like a Fourier series. So let's make this definition, that is n by L is, let's say, some number, some continuous thing, alpha of n, and then alpha n plus 1 minus alpha. If you use this definition over here, you will get pi by L, or delta alpha, the change in alpha, and 1 over 2L will be equal to delta alpha by 2 pi. So after making this few short definitions, now let use the Fourier series. So this is the Fourier series. Remember, this function f of x is expanded into its Fourier series, and if these Cn's, these Fourier coefficients, as you know, we have derived the formula for them. The Cn were equal to 1 over 2L minus L to plus L f of x e raised to power minus alpha n x dx. And if I now use these definitions over here and put it into the definition of Cn, you will see that this will change to something like this. One more change I have made is changing from x to u. This dummy variable for integration is changed from x to u to make it more to make the whole procedure more transparent. So you see now these Cn's are some integral of this kind, and now what I want to do is to put back the Cn over here, and when I do this, then f of x becomes looks like this. So I have just put the value of Cn after making this few definitions into the Cn, and then putting back into the value of f of x. And this is as you can see is equal to the this thing, and just I have made a minor modification, bringing it in here, and then making a definition of f of alpha n, this integral over here. We can write this whole f of x something like this: 1 over 2 pi minus infinity to plus infinity of alpha n d alpha delta alpha. So with the help of these simple definitions, you have seen that we have transformed this function expanded into Fourier series into something like this one. Yes, this is an important term. You see now it over here. So already it is emerging like something a Fourier series. Okay. So now if we let L goes to infinity and delta L alpha or pi by L is going to 0, and then this summation will go to the integral, because in this here in this formula everything is okay, but we have the summation. So summation is for the discrete case and not continuous. So we would like to change this to the integral form, and this we can do by making this definition, that is letting L go to infinity and delta alpha going to 0. Then we can replace this summation with the integration, and once we have completed this, and then replacing and substituting the Cn value into the f of x, you can see f of x is looking something like this. And if I put f of alpha value, which we have developed over there, and we get these two integrals, and then f of u and this exponential and du d alpha. And this can be simplified to look like 1 over 2 pi, as you can see that we have two integrations, so first integration and the second integration. So this is the f of x now have been transformed like this. So now if I define that the g alpha is this first integral, as you see. So if I define this to be g alpha, or make a little change of variables from x to u, so this second equality, you see it here. So then what will happen, that this f of x will be equal to this thing, and we have already you are already seeing that this is the definition we have made for the Fourier transforms. So these few steps were just to convince you that the definition we have made was really correct. So maybe you can go back to everything and check it back again, and you will see that this everything is quite nice over here. For example, we have made these few simple definitions, and then from this simple definition we have Fourier function expanded like this, and we have these coefficients, and we made a few definitions over here, and then we transform this summation into integration, and using these limits we were able to bring in here the definition of Fourier transform. And in a short way, it was a convincing proof that we have written the f of the Fourier transforms correctly. Okay, so this was the Fourier transform. But if you remember that in case of Fourier series, we have done the Fourier sine series and Fourier cosine series separately for even and odd functions. And similarly, we can do these Fourier sine transforms and Fourier cosine transforms as well for the odd functions and for even functions. So first let me show you the Fourier sine transforms, and it is very simple and straightforward, because we know the Euler formula, and Euler formula gives us that e to the power minus alpha x could be written as cos alpha x and minus sine alpha iota sine alpha x, and we can just put it into the definition of g of alpha, which is equal to 1 over 2 pi minus alpha to plus alpha, and you can just replace this exponential with the cos alpha and iota sine alpha. And here you see two important things. We are assuming that this f of x is an odd function, and remember that I told you that if you have a product of odd and even functions, what will happen. So this is odd and this cos is even. So we, in the first term, we have over here we have the product of odd and even, and in the second we have product of odd and odd. So you remember that the product of odd and even integrated was giving us value 0, so this will go away, and we are left with only the second term. So this one, because here we have odd and odd multiplied, so this will survive, and the first term will just go away. Okay, so then we can take bring it the sign of minus outside the integral, and we can write this g of alpha into this form. And then if we replace alpha by minus alpha, remember the definition of the odd function, that whenever you replace alpha with a minus alpha, you get the negative sign, and that is this was the definition of the odd function, that g of minus alpha is equal to minus g of alpha. And in this formula you have seen that when we replaced a minus sign with the plus sign, we get something outside as a minus, and this because f of x was really an odd function. So So from this, now you see that we have defined that f of s is equal to 2 by pi under root and gs into sine alpha. These are called the Fourier transforms. So this is the Fourier transform and this is its inverse, and you see that in these definitions we have made this factor split it between the transform and its inverse, so that it completely looks symmetric. So this is for the odd functions, and if we want to have similar transforms for the even functions, then we can have Fourier cosine transforms, as you can see here. These are just similarly defined, but now we have for these cosine functions. So this is the Fourier cosine transform and its inverse, but remember this is for even function. The Fourier sine transforms for the odd function, and this is for the even functions. Okay, so this was the definition of transforms, and then sine transforms and cosine transforms. Now it's time to give you a quick example for the Fourier transforms. And in this example we are taking a non-periodic function, and this is its sketch, and it's a non-periodic and is continuous. Maybe it's you can think of it physically just like an impulse. By, for example, if a ball hits the bat and there is a short impulsive force applied, then or you can think of a surge of current into a circuit. So these are all non-periodic functions, and we cannot represent them with the help of a Fourier series. So therefore we want to use for them the Fourier transforms and find out the and do the analysis. And it's very interesting that we can still do this analysis for the Fourier transform, using Fourier transforms for these non-periodic functions. Okay, in this case you can see that we have a non-periodic function expanded over here and sketched over here, and represented also mathematically. This f of x is equal to 1 into this interval, and 0 when x is greater than 1. And let's now apply the Fourier transforms to it, and for this non-periodic function. So first of all we have to calculate the g of alpha, which is equal to this 1 over 2 pi integral of f of x e to the power minus alpha x. And if you put the limits and put the value of f of x, you will get this integral over here, and it's very simple to solve to calculate this integral. So putting the calculating this integral and putting the limits, you get g of alpha equal to this thing, and then we put back this g of alpha value into f of x, and now we have the kind of integral defined for the f of x. Although this f of x, this function, was a non-periodic function and discontinuous, but we were able to use the Fourier transforms for it, and we were able to calculate g of alpha and put it back over here. And if you again try to simplify this, you can do this, and after the simplification you can see that this integral emerges over here, and this integral can be easily solved as well, and in order to get the complete value of f of x. And these are the references which you would like to have a look on, and at the end I would like to give you the summary of what we have done in today's lecture. So remember that the periodic functions and discrete functions we can deal with the help of Fourier series, and their different terms are actually the different harmonics or overtones in some physical problems or different frequencies. They correspond to them. But if we have a non-periodic and discontinuous functions, that we define Fourier transforms for them, and they are containing integrals, and therefore we can use them for continuous case, and we can accommodate the non-periodic one. So we have defined the Fourier transforms, and then I convinced you that these definitions were correct. And after that, we have also developed the for odd and even functions, the sines and cosines transforms. And at the end, I gave you an example where you could use the Fourier transform to evaluate the function f of x, and in some situation where non-periodic or continuous values were involved. With this, I thank you all.